Hey everyone, and welcome back. Ever feel like you're just swimming in AI updates, but maybe missing the really big shifts?
It's a lot to keep up with, for sure.
Well, today we're zeroing in on something pretty significant, a major figure in AI research, someone with, well, decades of experience.
A real heavyweight in the field.
Exactly. And they recently put forward a, let's say, surprising viewpoint about where things are headed, specifically with large language models, LLMs.
That's right.
Yeah.
Their main point, and it's quite a statement, is maybe, just maybe, the intense focus on just making LLMs bigger isn't the only way forward, or even the best way.
Right. So while, the big companies are pushing these models, adding more data, more compute, synthetic data,
Which makes sense from a product perspective. Incremental improvements are valuable there.
that this expert, they're suggesting the really interesting fundamental questions for AI research might actually lie elsewhere now.
Mm-hmm.
So our mission for this deep dive is to really unpack that thinking. Why the shift away from LLMs as the sole focus? And crucially, what are these more promising avenues they're pointing towards?
Okay, so let's start with that first part, that sort of cooling interest in purely scaling LLMs from a research standpoint.
Right.
The idea is that while scaling works for improving products, it might be hitting a point of diminishing returns for uncovering, the fundamental principles of intelligence itself.
So the really hard problems aren't necessarily being solved just by throwing more data at the current architecture.
That seems to be the perspective, yeah. It's becoming more about engineering and less about discovering fundamentally new things about intelligence.
Okay, so if not just bigger LLMs, then what? This expert highlights four key areas, right?
Four areas, yes. And the first one is a big one. Understanding the physical world.
How do you get a machine to have common sense about, gravity, objects, how things interact, not just based on text descriptions?
Exactly. Grounding AI in physical reality. That's number one. Number two is persistent memory.
Ugh, memory. So building AI that doesn't just react in the moment, but actually learns and retains information over the long term.
Precisely. Building on past experiences in a meaningful, accessible way, not just short context windows.
Makes sense. And the other two, reasoning and planning.
Yeah, and they're closely linked. The view here is that the reasoning LLMs do now,
Mm-hmm.
it's impressive in some ways, but maybe a bit superficial, like sophisticated pattern matching rather than deep, flexible reasoning.
So they think there are better, more robust ways to build reasoning capabilities.
That's the suggestion.
Yeah.
And flowing from that, better ways to enable AI to plan complex actions and sequences.
Okay, this really leads into the concept of world models, doesn't it?
It absolutely does. A world model is basically the internal understanding we have about how the world works.
Like, if I reach out to push this water bottle, I just know roughly how hard to push, what will happen. I don't need to read a description of it.
Exactly. You simulate it internally. And the argument this expert makes is that text alone, even vast amounts of it, probably isn't enough to build that kind of rich, intuitive world model.
Because LLMs fundamentally predict the next word or token. How does that help it understand the physics if I actually do push the bottle and it falls?
Right. That next token prediction paradigm might be limited for real-world interaction and understanding. It connects to how information is represented.
You mean tokens versus what?
Well, LLMs use these discrete tokens. Think of them like words or parts of words, maybe 100,000 possibilities in a typical model, a finite set.
Okay.
But the real world, sensory input, it's continuous, it's high-dimensional, it's not neat little tokens.
Like trying to describe every single shade in a sunset using only a few basic color words, you lose so much.
Exactly. And that's why early attempts to teach AI about the world by, say, predicting the next pixel in a video didn't really pan out.
Why not? Seems intuitive.
Because it's just too hard. Predicting every single pixel value is incredibly complex and, frankly, often unnecessary. Think about a video panning across a crowd.
Okay.
Can you predict the exact appearance of every single person's face in the next frame? Or the precise way a leaf flutters?
No way. It's fundamentally unpredictable at that level of detail.
Right. So systems trying to do that waste enormous amounts of computational effort trying to predict the unpredictable noise, the irrelevant details.
Ah, so it's inefficient and maybe misses the point.
Precisely. The more successful approaches, the ones this expert's focused on, involve learning more abstract representations.
Abstract, meaning not the pixels, but the concepts.
Yeah, learning the underlying structure, the relationships, the gist of what's happening, rather than reconstructing every single tiny detail. It's about capturing the essence.
Okay, so this leads to the proposed solution, right? These
Right.
JPAs and BJP.
Exactly. Joint Predictive Architectures, or JPAs. And VJP is a specific vision-based implementation. The core idea is to build world models that learn these abstract representations, particularly from video data.
So it learns about the physical world by watching videos.
Essentially, yes. But crucially, it's not just about watching. It's about learning to predict in this abstract space. If you show it part of a video clip, it learns to predict the abstract representation of the missing part.
Not predicting the exact pixels, but the concept of what should be there.
You got it. And because it operates in this abstract space, it can ignore all that unpredictable visual noise we talked about. It's much more efficient.
And this VJP model, it learns quickly.
That's one of the key advantages highlighted. Because it learns these fundamental concepts about the world during pre-training on video, it can then learn new specific tasks or recognize new objects with very few examples, often without needing massive fine-tuning.
That sounds powerful. Is this tech available?
Yeah, the researchers have actually released VJP publicly, which is great for the wider research community.
Okay, so it learns abstract representations from video. How does that help with understanding the world? Can you give an example?
Sure. Imagine training VJAPA on lots of short video clips of normal, everyday physics. Things falling, rolling, bouncing.
Okay.
It learns the rules implicitly in its abstract representations. Now show it a new video where something physically impossible happens, like a ball suddenly reversing direction in midair without anything hitting it.
Right, something weird.
VJAPA would try to predict the abstract representation of what happens next based on its learned model of physics. Because the weird event violates those learned rules, its prediction error in that abstract space will spike.
Ah, so it can effectively tell if a video looks physically plausible or not based on how well its internal model predicts what's happening.
Exactly. It develops a kind of intuitive physics engine based on observation, operating on these abstract concepts.
This sounds a bit like, Daniel Kahneman's System 1 and System 2 thinking. The fast intuitive versus the slow deliberate reasoning.
That's a connection this expert explicitly makes, yes. System 1 is that reactive, almost subconscious processing we do constantly.
Like catching a ball thrown at you. You don't consciously calculate trajectory.
Right. And System 2 is the slower, conscious, effortful reasoning, working through a complex problem step by step.
Okay, so how does that relate to current AI?
The argument is that most current AI, including LLMs, operates primarily at the level of System 1. They are highly reactive systems, good at pattern matching, and generating plausible continuations based on their training.
But they're missing the System 2 part.
Largely, yes. They struggle with tasks that require genuine zero-shot understanding and planning based on a deep model of the world. They can't easily reason through a completely novel situation from first principles.
But couldn't you train an AI to do a complex task through repetition?
You absolutely can. And this expert suggests that when you do that, when an AI learns a task through repeated execution, it's essentially compiling that complex reasoning down into a reactive policy, turning a System 2 process into a System 1 reflex.
Like learning to ride a bike. At first, it's all conscious effort, System 2. Then it becomes automatic, System 1.
Exactly that analogy. But to get that initial flexible, deliberate reasoning and planning capability, true System 2, this expert believes we need fundamentally different architectures, not just scaled-up reactive models.
So where does this leave the quest for AGI, artificial general intelligence?
Well, this perspective casts some doubt on the idea that simply making LLMs bigger and bigger will automatically lead to AGI.
Seems like a reasonable doubt if they lack these other core components.
Right. The future of AGI, if and when we achieve it, is much more likely to involve a combination of different systems and capabilities. Perhaps LLMs for language interface, combined with systems built on world models, persistent memory, and robust reasoning engines.
Sort of a hybrid approach. We're already seeing companies talk about omni models that handle different types of data.
Exactly. That trend aligns with this idea that intelligence isn't monolithic. It requires different kinds of processing working together.
There's also the data argument, isn't there? The sheer scale comparison.
Yes, that's a powerful point. Think about the amount of text data. LLMs are trained on numbers. Like 30 trillion tokens are thrown around. It's an almost unimaginable amount.
Someone calculated it would take like 400,000 years for a human to read that much.
Right. Now compare that to a human child. In just their first few years, they absorb a massive amount of sensory data, mostly visual and auditory, just by existing and interacting with the world.
Way more non-text data than text data, for sure.
The implication is pretty clear. If human intelligence relies so heavily on learning from rich, multi-sensory interaction with the physical world, then maybe training AI primarily on text is missing a huge piece of the puzzle. It might be an insufficient pathway to truly general intelligence.
It suggests that learning about the world through text is fundamentally different from learning from the world through experience.
Precisely. And that difference might be critical for developing the common sense, reasoning, and planning abilities we associate with higher intelligence.
Okay, this is a fascinating perspective shift. Thinking about these different architectures and the data needed, it underlines how crucial the underlying infrastructure is for any AI development.
Absolutely. And that actually brings us to our sponsor for this deep dive, StoneFly.
Hmm.
They're deeply involved in providing that critical data infrastructure.
Right. StoneFly has been around for a while, really innovating in data storage and management. They cover a lot of ground: SAN-A, NAS, S3 compatible object storage.
Backup and disaster recovery, cloud integration, and they're also integrating advanced AI and security tech into their solutions. It's quite comprehensive.
And it's not just the storage itself, but the services around it. Things like immutable snapshots, which are vital for data protection, right?
Critical, especially against ransomware. Plus, strong AES 256 encryption, both for data sitting on the disk and when it's moving across the network.
They also offer replication options synchronous, asynchronous, for keeping data safe across different locations.
And smart features like intelligent tiering to manage costs, flash caching for performance boosts, and specific ransomware volume protection. It shows they're thinking about modern threats.
They even have a patented, immutable, and air-gapped repository. Air-gapping is still a gold standard for serious data protection.
Definitely. Add to that their resilient architecture, things like control and node, constant mirroring for high availability, and the ability to manage it all, potentially up to 128 nodes across different sites from one interface. That's key for manageability.
That patent for the immutable and air-gapped tech really highlights their focus on security and recovery.
It does. And they've got industry recognition too. DCIG awarded them as one of the top 5 storage companies across SAN, NAS, and object storage. Getting ranked highly in all 3 is pretty impressive.
So for listeners who might be thinking, okay, I need better data protection, or we need to expand our storage, or how do we improve performance and scale?
Or maybe they're looking to refresh their infrastructure for backup, DR, hyperconverged systems, servers, VMware, Hyper-V, Proxmox. StoneFly positioned themselves as offering competitive pricing and strong support for all those scenarios.
And they have some specific offers running now.
Yeah, a couple of interesting ones. There's an entry-level $10 immutable and air-gapped backup option to get started,
Okay.
and then a more substantial 70-terabyte backup and disaster recovery appliance, which they note is expandable up to 4 petabytes. It includes those air-gapped and immutable features and works with common backup software like Veeam, Rubrik, Commvault.
And you mentioned an AI appliance.
Right, an advanced AI appliance featuring their object lockdown technology specifically for ransomware protection, available for $700. Seems geared towards enhancing security using AI techniques.
Got it. So if any of that sounds relevant, the place to go is stonefly.com.
That's the main site, stonefly.com. And for specific product or service inquiries, they list sales at stonefly.com.
Okay, good to know. Stonefly.com and sales at stonefly.com for advanced data storage and protection.
All right, so circling back to wrap up our main discussion, we've really explored this significant viewpoint from a leading AI researcher.
Yeah, the core idea being a shift away from just scaling LLMs.
Right. Moving towards architectures that can genuinely understand the physical world, maintain persistent memory, reason more deeply, and plan effectively.
The argument being that these capabilities are probably essential for reaching the next level of AI, maybe even AGI, and likely in combination with LLMs, not necessarily replacing them entirely.
It's about building a more complete toolkit for intelligence, not relying on just one type of hammer.
So the provocative thought to leave everyone with is, how might this shift actually change things? If AI moves from being primarily text-based to systems that learn and reason more like humans do through observing, interacting, abstracting.
What does that unlock? What are the real-world implications across industries in our daily lives if machines gain a deeper, more grounded understanding of the physical world and can act intelligently within it?
That's a huge question. Definitely something to ponder.
It really changes the landscape of possibilities.
Well, thanks for diving into this with us today. As always, we encourage everyone to keep exploring, keep learning as this whole field just keeps evolving so rapidly.